All right. Hello. We are Group 6. This is for electrochemical based machining. My name is Marcos Martinez Rodriguez.
My name is Noel.
I'm Nati Medrano.
Jonathan Morales.
And I'm Frederick Mushimoto.
Now to do the introduction. Electrochemical machining, also known as ECM, is a non-traditional machining process where material is removed from a workpiece by anodic dissolution in an electric cell, essentially dissolving instead of cutting the material. Due to this process, removing material by dissolution, essentially without mechanical contact or high temperature, it avoids heat, mechanical, and edge damage. ECM was initially developed to machine hard materials, although it is now used to machine any type of material. This process also has the added ability to manufacture complex shapes. Therefore, it is used in a variety of industries, such as mechanical components and electronics, which will be discussed later. Principles and properties of ECM. ECM works by workpiece acting on as an anode, while the shape tool acts as a cathode. Between them is a conductive electrolyte, usually some type of salt solution, uh, powered by a DC power supply, uh, which carries current through. The salt solution is usually NaCl. To continue this part, the process is based on Faraday's law of electrolysis, which states that the material removal rate, or MRR, also known as just the V, is directly proportional to both current and time, as seen in the equation V equals C I T. C meaning the specific removal rate for material that is being used on, I being the current, and T equaling the time. Again, this will be developed more later on. We want to maximize the removal rate. Therefore, it is crucial for us to maximize the current. Uh, this is where the quality of the process depends on the amount of current. The current I can depend on different factors such as the voltage applied, the electrode gap, which is the distance between the tool and the workpiece, and the electrode conductivity.
I'll be introducing the process for ECM. First, the tool will be shaped to the desired geometry. So, the second process will be both tools and workpiece are placed very close to each other, roughly 0.25 millimeters apart. Well, then a DC voltage is applied across both pieces around 5 to 30 volts and hundreds of thousands of amps are applied with the workpiece connected to the positive side and the tool connected to the negative side. Electrolyte is pumped through the gap at high speed. Then a metal ion from the workpiece dissolves into electrodes and are removed before they can deposit onto the tool. The workpiece then gradually takes the shape of the tool. Here we
Now to
provide a
do the
schematic
introduction.
of the process. We could see that a DC power supply is connected to a workpiece at the bottom and the tool where the workpiece is the positive side and the tool is the negative side. We also see a tank full of electrolytes connected to a pump, which is cycling the electrolytes into the tool. Some advantages and disadvantages of ECM. Advantages are high pressure precision, can achieve complex geometries with minimal distortion. So, it also could provide long tool life. The process can significantly reduce the tool wear, which will lead to a longer life. Also, no mechanical stress. ECM does not involve mechanical abrasion, which reduces the risk of damaging the workpiece. Some disadvantages would include high initial costs. The equipment and power supply required for the ECM is expensive. Slow processing speeds. ECM is all slower compared to traditional machining methods. And limited materials. Non-conductive materials such as plastics or ceramics cannot be machined since they are weaker compared to metals. Some applications will be including aerospace, medical devices, automotive, and electronics. Some applications in aerospace would include turbine blades, engine parts, and fuel nozzles. Applications in the medical field will be stents, surgical instruments, and orthopedic implants. In the automotive field, it will include fuel injection parts, gears, and in electronics will be sensors, circuit boards, and connectors.
I'm going to be introducing several common techniques used in electrochemical machining. Conductive grinding is a variation of ECM that uses a grinding wheel as the cathode, allowing very precise and controlled material removal. Electrochemical polishing focuses on smoothing the surface by removing tiny high points to create a clean, polished finish. Electroplating does the opposite. Instead of removing material, it adds a thin layer onto the workpiece through electrolysis. And finally, etching uses anodic dissolution to selectively remove material and create pattern or design on the surface. These techniques highlight just how versatile ECM can be depending on the application. So for a couple of specialized techniques ECM methods use, there's pulse ECM, which uses pulsed direct currents to produce finer detail and more controlled material removal. There's also micro ECM, which operates on a small scale and is used for tiny, precise features in electronics, medical tools, and aerospace components. There's also hydrodynamic ECM, which improves the process by using a high velocity electrolyte stream to enhance efficiency. And there's also smelting, which while not being an exact ECM technique, it's included here as another electrical based metal process, very similar to ECM. It melts the metal using high heat and electrical current for large scale refining or production. Okay, so electrochemical machining is used across multiple industries, as kind of talked about earlier. We're just gonna go into more detail about these. For example, aerospace. It helps produce highly precise and complex components such as turbine blades, engine parts, and fuel nozzles. In the medical field, ECM is used to manufacture stents, surgical instruments, and orthopedic implants where accuracy and smooth surfaces are essential. And in the automotive industry, ECM helps create fuel injection components, gears, and other parts that require tight tolerances and consistent performance. Um, for some more real world examples, in electronics, for example, it's used to create small connectors sensors, and circuit components with high precision. It is also used in jewelry making because ECM allows for very intricate and delicate designs in metals like gold and silver. And in the energy industry, ECM is used to produce turbine blades, boilers, and heat exchangers, thanks to the process's ability to handle complex shapes and hard to machine materials.
Here, now we're going to talk about the equations often used when dealing with electrochemical machining. This one here is to calculate how much material was removed during the machining, V being the volume of the material once that was removed. C is the specific removal rate, and this is material dependent. So it is different from material, and you would have to either search it up or look at a table like the one shown on the right. I is the current in amps, basically how much power the machine is using. And T is how much time the machine used. Then here, some of the parameters that we have. This one, the first equation here is resistance, big R being the variable for resistance. G is the gap between the electrode and the material that you're machining. R is the resistivity, and A being the area of the electrode. Then I is to calculate for the current. And here, the only new variable is E, which is the voltage. And this one, the feed rate equation, basically how fast the machine is fed material, F being the rate, C being the removal rate. Again, you would have to either search that up or look at a table shown a couple of slides ago. I being the current, and A being the area of the electrode. Now for a quick example, an electrochemical machining operation is used to cut a hole in a plate of aluminum that is 12 millimeters thick. The hole has a rectangular cross-section, 10 millimeters by 30 millimeters. The operation is accomplished at a current of 1,200 amps, and the efficiency is 95%. And the question is asking us to determine the feed rate and the time it took to cut through the plate. So first things first, we try to find the feed rate, and we just do that by plugging in all of the numbers for the feed rate equation. First off, we have to define C for the specific removal rate, and looking at the table on the right, it is about 3.44 times 10 to the negative 2. Then for the current, which is given, so 1,200 amps, and then we divide by the area, which is calculated to be 300 millimeters, which we got by multiplying the 10 millimeters by 30 millimeters. And we end up getting a feed rate of about 0.1376 millimeters per second. But since it's at an efficiency of 95%, the real feed rate is 90.95 times what we calculated before. And so our actual feed rate is 0.1307 millimeters per second. To calculate the time it took to machine through the 12 millimeter plate, all we do is take the thickness of the plate, which is 12 millimeters, divide that by our actual feed rate, which we calculated to be 0.1307 millimeters per second. After dividing, we get 91.8 seconds, or about 1.53 minutes to cut through the plate.
So, when it comes to handling any type of machinery, safety is always something that should be practiced. Even if the machinery is not inherently dangerous, even if there isn't any sharp objects or any obvious safety hazards, there could be an adverse effect that are not visible or obvious to someone. There could be environmental hazards such as gases or vapors. So this is why safety precautions are a must. And in the following slides, I will explain what precautions one must take, what gear one should use, and how the machine should be maintained before starting the machining process. So, safety equipment. What safety equipment do you need to keep yourself safe? Well, since we're dealing with chemicals, splash protection is a must. So that includes gloves that are rated for the chemicals used, and goggles to protect and cover your eyes, shoes that cover your entire feet, and long sleeves in case any chemical spills. Other personal safety needed is a respirator for the fumes or vapors that may be produced by the process to protect your lungs. All of these are must for proper safety, and oneself should always be all of this should always be worn when around the machine, not just when operating it. Now, personal safety isn't the only factor. If the lab isn't also accommodating, one may as well not have any protective gear on. So, how should a proper safe lab look like when dealing with electrochemical machining? Well, first, the machine should be properly set up. This means proper grounding, given the machine uses electricity in the machining process. Proper grounding for the machine to operate properly is also necessary. The second measure is short-circuiting prevention. Since the process uses water and electricity, the machine should be able to detect any shortages that may happen and stop or warn about them. Third is waste management. The process of electrochemical machining can cause waste that must be dealt with safely. Fourth, when the machine is operating, it is important to keep an eye on it to allow for any interference in case of any malfunction. And lastly, the environment must use proper ventilation in order to ensure that the fumes do not linger or cause harm. So, we hope that this introduction to electrochemical machining has educated you on the process that goes into producing parts, when it's appropriate to use, and the uses for everyday life. Here are some takeaways and that we hope you will understand from this presentation. So for everyday uses, we hope that you see that electronics use circuit boards and connectors, and in the automotive industries, gears are used, and surgical instruments are produced in medical fields using electrochemical machining. And we also hope that you understand when it is appropriate to use. Electrochemical machining is best used when a high precision, durable part is needed, remembering that material used must be conductive in order for the part to be machined, and the expensive and slow production rate is also taken into accommodation. Thank you. That is all.